Assalamu alaikum, brothers and sisters. Welcome to the journey of quest, where we quench your thirst of knowledge. Have you ever wondered why diamonds sparkle or why metals bend? The answer lies in lattice defects. Picture a perfect crystal lattice, an ordered array of atoms or molecules. But the reality is, this perfection is seldom found in nature. In fact, defects or imperfections in these lattices are what give materials their unique properties. These lattice defects are like the secret ingredients in a recipe, adding flavor and character to the materials around us. They impact the hardness of a diamond, the malleability of metals, the electrical conductivity in semiconductors, and much more. In this video, we're going to explore this hidden world of lattice defects. We'll delve into the three main types: point defects, line defects, and planar defects. Each type has its own fascinating quirks and roles to play in influencing the properties of materials. If you're ready to dive deeper into the fascinating world of lattice defects, stay tuned. Imagine a perfect crystal lattice. Now take away an atom or add an extra one. What do you have? A point defect. This is not a flaw or a mistake, but rather a fascinating phenomenon that has substantial effects on the properties of materials. Point defects, as the name suggests, occur at a single point in the crystal lattice. They are essentially deviations from the ideal arrangement of atoms in a crystal structure. There are three main types of point defects we're going to look at: vacancies, interstitials, and substitutional defects. The first, vacancies, are pretty straightforward. Imagine a seat in a movie theater. Now imagine that seat is empty. That's a vacancy. In the context of a crystal lattice, it's an atom-sized seat that's missing its occupant. This can occur naturally during the formation of the material, or can be induced by external factors like temperature. Next up, we have interstitials. These are the gatecrashers of the atomic world. They're extra atoms that have squeezed themselves into the tiny spaces between the regular atoms in the lattice. Like a person standing in the aisle of the theater, they're not supposed to be there, but there they are, disrupting the normal flow of things. Finally, we have substitutional defects. These are a bit like a case of mistaken identity. In this scenario, a foreign atom replaces a regular atom in the lattice. It's as though someone else has taken your seat in the theater, and they're not the same size or shape as you, causing a bit of a disruption. These point defects can significantly affect the properties of materials. For example, they can impact electrical and thermal conductivity, mechanical strength, and diffusion rates. They can even be beneficial, allowing us to tweak and tune the properties of materials for specific applications. So in a nutshell, point defects might be small, but their impact on material properties is significant. Now, imagine a row of atoms in the lattice going awry. This introduces us to line defects. Line defects, also known as one-dimensional defects, occur when the regular arrangement of atoms or ions in a crystal lattice is disturbed along a line. This disturbance can be as simple as a row of atoms being slightly out of place, or as complex as a string of atoms being entirely missing or extra. There are two main types of line defects: edge dislocations and screw dislocations. Let's start with edge dislocations. Picture a half plane of atoms inserted into the crystal structure. The atoms above the extra half plane are squeezed together, while those below are pulled apart. This creates a line of defect or dislocation line running perpendicular to the direction of the extra half plane. Edge dislocations can dramatically affect the mechanical properties of materials, often making them more malleable. Now let's move on to screw dislocations. This type of line defect occurs when a shear stress causes one part of the crystal to slide past another. This results in a spiral stair-like arrangement of atoms around the dislocation line. Screw dislocations are fascinating because they allow for plastic deformation. That's the permanent deformation of a material under stress, without the need for large forces. Both edge and screw dislocations can move through the crystal lattice. This movement is what allows materials to deform plastically, which is crucial for many applications. For instance, the malleability of metals, which allows them to be hammered into sheets or drawn into wires, is largely due to the movement of dislocations. However, it's important to note that while dislocations can enhance the deformability of materials, they can also weaken them. Too many dislocations can lead to the material becoming brittle and prone to fracture. Line defects, although more complex, play a crucial role in the deformability of materials. Finally, picture a whole plane of atoms missing or misplaced in the lattice. This brings us to planar defects. Planar defects, as the name suggests, occur over an entire plane within a lattice. Imagine you're building a brick wall and suddenly a whole row of bricks is missing or misplaced. That's a planar defect in a nutshell. This is the largest type of defect and has a considerable impact on the properties and behavior of materials. There are three main types of planar defects: grain boundaries, twin boundaries, and stacking faults. Let's delve into each of these. First up, grain boundaries. These occur when crystals or grains in a material form at different times and orientations. The area where these grains meet is the grain boundary. These boundaries can impede the movement of dislocations within a material, thus strengthening the material. Next, we have twin boundaries. These are unique and interesting. Imagine a mirror reflection of the atomic arrangement in a lattice. That's what happens at a twin boundary. The atomic arrangement on one side of the plane is a mirror image of the arrangement on the other side. This can happen during the crystal's growth or due to mechanical stress. The presence of twin boundaries can enhance a material's ductility. That's its ability to deform without breaking. Lastly, we encounter stacking faults. Picture a deck of cards. Now imagine if one card was slightly out of place, disrupting the perfect stack. That's a stacking fault. It's a disruption in the sequence of atomic layers in a crystal lattice. Stacking faults can alter the electrical and optical properties of a material, making them a key player in semiconductors and optoelectronic devices. So you see, planar defects, while they might sound like a problem, can actually be beneficial. By influencing the mechanical, electrical, and optical properties of materials, these defects play a crucial role in the functionality of many devices we use today. Planar defects, the largest of the three, significantly influence the properties and behavior of materials. So, we've journeyed through the world of lattice defects, from tiny point defects to expansive planar defects. Let's take a moment to reflect on what we've learned. We started with point defects, the simplest form of lattice defects. These are irregularities that occur at single points in the crystal structure. They're like the lone wolves of the defect world, choosing to go it alone. Point defects can alter material properties in fascinating ways, like changing the electrical conductivity or even the color of a material. It's like having a secret superpower that can be activated by the tiniest tweak in the structure. Next, we explored line defects or dislocations. These are a bit more complex. Imagine a misalignment or an extra row of atoms in the lattice structure. It's like a traffic jam on the atomic highway. These dislocations can significantly influence the mechanical properties of materials, making them more malleable or ductile. They're the architects of change, enabling materials to bend and twist without breaking. Finally, we delved into the world of planar defects. These are large-scale disturbances that occur over an entire plane of atoms. Think of it as a boundary or a wall within the material. Planar defects can have a profound impact on the properties of materials, influencing their thermal expansion, magnetism, and even their chemical reactivity. They're the gatekeepers, controlling how atoms move and interact within the material. But here's the thing to remember. These defects aren't flaws or mistakes. They're essential aspects of the material's identity. They shape how materials behave, how they react, and how they change. Remember, the beauty of materials lies not in their perfection, but in their defects. After all, it's the lattice defects that make materials more than just a collection of atoms. Thanks for watching us share our videos, subscribe our YouTube channel, and press the bell icon, and stay curious for new uploads.